Okay, quick introduction of Deirdre Des Jardins. I became aware of her through her, actually through her tweets, something good about Zitter, and really enjoy her account and updates on climate science and weather and that intersection. So Deirdre has conducted research and advocacy on climate adaptation in the California water sector since 2010. She has a research background in nonlinear dynamics and complex systems theory, previously worked with research teams at NASA Ames, the Center for Nonlinear Studies at Los Alamos, and the Santa Fe Institute for Complex Systems. With that, I will give it to you and tell us about why we're in hot water.
Here I am sharing my PowerPoint, and I didn't come up with this title, but I love it. Yeah, in hot water. We are absolutely in hot water. And Antonio Gutierrez, the Secretary General of the UN, started talking about global boiling. And this is why. This is a map of sea surface temperature anomalies this year, and it's in units of standard deviations. And you can see that it's not only the equatorial Pacific where we normally get abnormal ocean temperatures, ocean temperature anomalies, but also the North Pacific, and it's very warm off the coast of Japan here, as well as the Atlantic and parts of the Arctic Ocean as well. And Dr. Jennifer Francis is a polar scientist and climate scientist who I deeply respect. And she said about this year, expect chaos. She said, we have not had a strong El Nino in conjunction with an ocean heat wave in the North Pacific, in conjunction with an Atlantic Ocean where the temperatures are almost off the charts. This combination of factors is really nothing that we've seen before. And so it's a real challenge to make any kind of a prediction. But she did say we should expect chaos. And so far, it's been a year not only for extreme heat waves, but also for extreme flooding. And Twitter has just been exploding. If you're following weather accounts or climate accounts, there been extreme flooding in Greece, Turkey, Libya, Hong Kong, Shanghai, Spain, and Las Vegas. And that's just in the first part of this month. As you know, there was flooding earlier, and we had Hurricane Hillary in August. So it's been an extraordinary year. Just to give you an idea, Greece got 2 years of precipitation in 48 hours. And I'm showing that this is from Meteo, Greece, which is the Greek weather service. And they're showing flooding in the Thessaly Plain. It's one of the flat areas of Greece. 72,000 hectares, which is about 178,000 acres, is flooded. And then there's another flooded area. It's 22% of all of the agricultural land in Greece. Hong Kong got over 6 inches of rain in an hour. And they had extreme flooding there. So it's a concern And what's been causing it is the warm sea surface temperatures. The sea surface is warmer and the atmosphere is warmer. And so there's just a lot more water vapor in the atmosphere. And when the atmospheric conditions get set up right, you can just dump all that water. And that's partly what happened in Greece. Was the Mediterranean Ocean has been anomalously warm. And they also had a storm that kind of stalled over Greece. And so it just was dumping enormous amounts of water. This is just to give you an idea of the overall trend in atmospheric moisture. This is global trends in atmospheric moisture from June through August, which is kind of the hurricane season. And it's been going up, and we're at about fourth highest in the observational record. So it's, it's climate change, it's global heating. And this is kind of a complicated diagram, but I really liked it. So this is, what are the different processes around the world? And you can see the green bands are where, those are the hurricane bands, and those are where you get tropical cyclones. And so a lot of the flooding in the tropical cyclones tend to occur in the summer and fall months. And so the peak in west of Mexico is June to October. The peak for hurricane season in the Gulf is August to October. So a lot of the extreme flooding we've been seeing this summer has to do with juiced up hurricanes. But what's more important is that big orange arrow aiming at California, and that's atmospheric rivers. And we're not the only, the west coast of North America is not the only region in the world that gets atmospheric rivers. They also hit the west coast of Europe, the west coast of South America and Chile, west coast of Australia. But we're one of the areas in the world that gets the most atmospheric rivers. These orange circles are the number of landfalling atmospheric rivers and in days per year average. And so you can see, we're kind of a hot spot in the world for atmospheric rivers. And the moisture comes in from the Pacific. So I want to go to another map, and this just shows the various coastal regions that get atmospheric rivers, and we're region 3 in this map. And this is another nice study. It came out of Spain. Remember what? And I was like, why is Spain studying atmospheric rivers? Well, it turns out they stick out into the Atlantic there, and they get smacked with atmospheric rivers coming across the Atlantic. So there's been, for these atmospheric rivers all over the world, there's been, these researchers in Spain found an increase. It's been trending upwards since 1980, and it kind of goes up and down a little, but generally it's been upwards. Well, the issue is atmospheric rivers on the West Coast have had very little trend. And in some sense, we've been sort of protected from this trend. And if you look, the maximum 3-day precipitation from atmospheric rivers on the West Coast has actually been going down. And so why is that? And could it change this year? And that's why this research done by researchers in Spain is really important. So they took air parcels and they had a computer program that could track the air parcels backwards. They would take air parcels from the atmospheric river that were dumping rain, and they used data. They ran them backwards, and they found out where in the ocean the air parcels were picking up moisture. And they did this for regions all over the world. This one, it's a little hard to decipher because it's the west coast of North America, but it's kind of polar. But this is the west coast of North America, and this blue region, which is north of Hawaii, is where we get our moisture. And for the atmospheric rivers that come slam into the mountains and dump a bunch of rain. So this is what the sea surface temperatures have looked like since the end of the 97-98 El Nino. And it kind of flipped. So there's these cooler patterns of sea surface temperatures in kind of a horseshoe pattern, and particularly near the coast of California. And for transporting moisture, the last couple of 100 miles really matter. So in some sense, that's protected us from having the same kinds of huge increases in anomalous moisture that we had before. And in fact, if you look, this is the precipitation anomaly. Not only is that pattern associated with less maximum precipitation, it's associated with less precipitation overall. And we've had this drying trend since the 98, 99, 97, 98 El Nino. And this was actually changed. It's called the Pacific, this horseshoe pattern. It was kind of a flip from this horseshoe pattern of warm temperatures near the coast and cool temperatures in the central North Pacific that we had from 1977 to 98. And that 97-98 period was associated with more precipitation in January, February, and March. And in fact, we had some huge floods when we had warm ocean temperatures near California, near the west coast of California. So you can see we could flip back to something more like this. We could get something more like the floods of 82, 83 and 97, 98. We don't know. And the reason is this pattern isn't like the historic pattern from 77 to 98. This is, huge amount of global warming on top of what would normally be a flip to what's called a warm Pacific decadal oscillation pattern in the North Pacific. And so we don't know. Our best, we do know the ocean temperatures for the entire world are off charts. They're over 2 standard deviations above normal. And so we may be seeing a long-term shift in weather. This is the best guess. What we have is our computer models, and this is the best guess we have for what precipitation rates are going to do next January through March, which is when the zonal winds that sweep across the Pacific. The models are also forecasting those could be favorable towards hitting us with a series of atmospheric rivers. So you can see the highest projected anomaly is in Southern California, but there's also precipitation rate anomalies projected for the rest of California. So we don't know, and this is long-term out, that's why it only is giving chances of above normal. We're gonna have to see how it evolves. The models do better the closer you get to the time period. But I'm recommending that people prepare for the possibility of flooding like we saw in 82, 83, and 97, 98. Because I think based on this, the risk is absolutely there. We just don't know. We don't know how it's gonna fall. The other thing I wanted to say, kind of hitting you with a lot of information, but there was a new analysis of ocean temperature data, and it's really striking. This trend, I'm like, why are the oceans everywhere suddenly so warm? Is this a long-term thing? And the fact is that it's not just the top layer of the ocean that's been warming, but some new analysis shows, yeah, the middle layer has been warming. And even the deep layers, in particular, the deep layer of the Southern Ocean and Antarctica has really been warming. So the entire ocean column is warming across a lot of the planet. And so this is not just a blip. I think it's a start of kind of the climate shift towards much warmer sea surface temperatures. And what happens is you'll have in these changes where the ocean is absorbing heat, and we had that in the first decade of 2000s. After the 97, 98 El Nino, and it discharged all this heat. It was cool for a while, and we didn't have an increase in ocean temperatures. But then it started to go up again. We're ratcheting up, so we're going to see warmer and warmer ocean temperatures. And I don't think this kind of flooding is a blip. And over the long term, it's going to hit California. So I wanted to share, this is European researchers did this study, and it's where daily rainfall records were deviated from that expected in the stationary climate. In the blue areas, you can see Europe, Brazil, India, South America, just about everywhere except for the west coast of North America and the tip of South Africa have been having trends towards increasing daily rainfall records. And I think we need to understand the reasons better why California and west coast of North America hasn't seen that. But I think there's a line of evidence, which I just laid out, that it's tied into ocean temperatures being cooler, and that's changing in the North Pacific. And this is something I absolutely think California needs to be putting more money into researching as well. There's been a lot of hand waving that, oh, this is natural variability, but it's not natural variability anymore. And we're having these huge temperature anomalies. And there's a lot of discussion about this. And climate scientists are starting to discuss, climate shifts. There'll be a lot of research coming out this year. But what we need to do was done by the U.S. Geological Survey. We need to do some risk assessment modeling, and we need to look at what happens if we have extreme precipitation in California. And the U.S. Geological Survey, as part of their science applications for risk reduction program, did the first ARC storm study back in 2010. And this is a map of where their simulation showed you could get extreme precipitation. It's in Southern California and along the Sierra Nevada. And the problem is the flooding was so catastrophic and so overwhelming that most locations, most counties and most cities in California have not incorporated it into their hazard mitigation plans, even though the scenario was specifically designed for emergency response. We know that with extreme flooding, one of the key things to do is to get people out of the way. It's really stunning to me that there's been so little incorporation of this scenario in emergency response plans. But I've talked with the folks who did the study. There's just been a lot of resistance because it is pretty overwhelming, particularly if you look at the Central Valley or the Tulare Lake region about how much flooding there is. But what happened this past winter with the Tulare Lake region could be just a foretaste of what we could see. And we really need to start grappling with it. And I like to quote Wallace Wells, who said after the extreme flooding in British Columbia in 2021, we aren't just failing to address the growing climate crisis to come, we're unprepared even for the impacts already here, in part because they keep surprising us with their intensity, and in part because we can't seem to fathom their genuine vulnerability. So that's my presentation.
Usually at this point, we look for the sugar coating, but
I don't sugarcoat. And
no,
right.
it's, I don't think, no, I can't say that I'm a big fan of the "is what it is" phrase, but yeah, I don't think sugar is appropriate here. As a matter of fact, one of the things I want to do after this event is actually learn more about Libya and the flooding there. I thought I was up to date on Morocco maybe, but then the Libya thing looks awful. And so there was some mention of that earlier today about dams breaching and yeah, sounds catastrophic. In a dry climate, checking on, I don't see questions at this point. I think this is just something we're going to have to point to as a recording and have people review, because we did have a long format, a wet talk with Daniel Swain talking about arc storm, the arc storm scenarios, and since then I think it's now in the 2.0. I still think there's denial in a lot of those projections, as you pointed out, and we're facing a very different winter than last winter. Yeah, apparently.
Daniel is, I highly recommend people follow him, and he is he is just a great wizard of atmospheric science, and he's following us very closely. I will say that Daniel has been trying to get funding to do the next phase of Arc Storm 2.0, and not only do modeling of where it would flood, but also to do tabletop disaster scenario exercises. And I was very sorry to hear that University of California got $100 million for climate adaptation studies, and they didn't fund his proposal. And,
They gave it to the football team.
yeah, they gave it to some collaborative thing with the Delta Science Program and the Department of Water Resources and multi-agency. But Daniel is looking at extremes. He looked at extreme drought and extreme precipitation and extreme flooding. And that's where the best available science is leading us. And we've got to find ways to fund science.
Yeah, no, I certainly agree. A question from Brian Schmidt popped up. I don't know if you see it in the Q&A here. In a desperate attempt to poke holes in Deirdre's presentation, is it too much to draw conclusions about the current super high ocean temperature when it's just a single year that's so different from the rest? I know we still have a problem regardless. So I'm not sure what step of grief that is, but
let me say that it is likely that we'll have some plateauing. So El Nino, what happens is during La Nina, there's upwelling of cool water in the Eastern Pacific, and a lot of heat gets absorbed into the upwelling water. And then in El Nino, that reverses, and there's a lot of discharge of heat in the equatorial Pacific. So yeah, some of that will reverse and we'll have sort of a plateau. But what was happening is we're stair-stepping up. So, it's like the temperatures go up, then it plateaus, and then it goes up again. And what we don't know, the thing that's anomalous this year is the record warm sea surface temperatures all over the planet. And Trenberth, who's did foundational research on the Pacific Decadal Oscillation, says he thinks the global ocean, like the North Pacific, during these cooler periods of the Pacific Decadal Oscillation, the North Pacific is storing heat below 300 meters depth, and then it's emerging. So we've been storing a lot of heat in the ocean, and that's why I threw in sort of this picture of the entire ocean column is warming. So we're not gonna return to a 20th century ocean temperatures. It's going to keep stair-tapping up, and we really are in a climate emergency.
By the way, what in terms of ocean temperatures in coastal, like to some degree off the coast of California, obviously the Monterey Bay is very deep and has been traditionally very cool because of that, and a lot of things off the Pacific are generally cooler than, say, the Florida Keys or something. And just taking that kind of view, a pretty narrow view of the California coast, yeah, I see.
So these are anomalies. So when you look at absolute sea surface temperatures, the upwelling along the California coast, it's still cool, but off the coast, people were reporting that the ocean was 64 degrees, and it does peak in August, but normally it peaks at around 60. So it was anomalously warm for California. And one of the things that can happen is there's a mixed layer on the ocean, top of the ocean, that that exchanges heat with the atmosphere, and if it's warm and still, the mixed layer can get thinner. And in fact, it does get thinner annually in summer. And then when there's lots of storms churning it up, it gets deeper. But it can get very shallow and then it can warm rapidly. And that happened probably in the Atlantic, where they've had a huge amount of warming over just a few days. So one of the things that happened, there's been these warm anomalies in the Northeast Pacific in recent years, and that's related to this, they call it shoaling when the mixed layer gets shallow, but the mixed layer was record shallow in this large area in the Northeast Pacific. So
yeah, I was thinking of the just even in terms of ocean depth and thinking of like Monterey Bay versus off the coast of Massachusetts and that area of New England, which is relatively shallow. Are there now again that area looks so I could tell looks pretty red. And that's been an area with just I know famously with can have, because it's so relatively shallow, can is affected by big storms as well. So
part of this is, so let me talk about it a little bit. So some of it has to do, there's cooling, it's called Antarctic bottom water formation, but in the Antarctic, there's very cold water that forms and goes north. And it's part of the, there's a global overturning circulation, meridional north to south overturning circulation. The Atlantic meridional overturning circulation is better known, but there's also a circulation of cool water north from Antarctica. And what's happened is 68% of heat content that was going into the ocean was going into the Southern Ocean. And you can see the kind of warming that happened there. And this new analysis by these two scientists, Bagnall and DeVries at Santa Barbara, is incredibly significant for that reason. I think because they showed this, it's very hard because there's very, very sparse data, but they used a new machine learning method to interpolate the sparse data, and they found really rapid warming. It's less in the Pacific. And what you're seeing is if you look at the deeper ocean, there's less warming. It's more recent warming in the Atlantic. The Pacific was actually cooling for a while, and the Pacific actually has memory of the little ice age, which ended the middle of the 19th century. But it takes that long, they're still in the very deep waters, there's still cool water that was cooled in the little ice age. And what's happening when you look at what happened with the Pacific here in the deep water is there was a cooling trend for a while. The currents were such that it was cooling and the middle layers were cooling, and now they're warming. So when we had that global warming hiatus, part of what we were doing was heat content was going into the middle and deep layers of the Pacific. And if you find that terrifying, I apologize, but
I kind of do, yeah.
Yeah.
So I think I could talk for a much longer time, but I think I think it would be wise to call it quits and for today. And keep up to date with these things. And by the way, if you're social media, what is it?
Oh, it's
You
flowing
have it up there.
uphill. Flowing uphill. I named after
Yes,
Mark
flowing
Twain.
uphill. That yes, I
Yeah.
remember it was pretty memorable. And it
Yeah.
yeah, hot water flowing uphill. And so thanks for coming and not sugarcoating. It's yeah, it's hard to yeah, it's hard to this would be a tough job to apply sugar to. So but we'll have to see how this impacts us even in the short term, in the winter. Hopefully not well, we're going to definitely test out emergency systems and
Yeah.
water channels and levees and all that fun stuff
I'm
to
really
some degree.
glad in a way that we had, the wake-up call this past winter, because people started realizing, well, maybe the counties aren't as prepared as we thought. So this absolutely is about emergency response and preparedness and about long-term thinking. But I mean, there's a lot of talk about collaborative solutions and progress towards things, but we unfortunately, there's some really kind of rapid acceleration of of these kind of extreme events, and it's taken all of the climate scientists by surprise this year. People are just stunned. And so we've got to get better about communicating risk as well. And that's what I'm trying to do. And, I get around in the literature and understand what's going on and communicate with the scientists and try to communicate it to people. But yeah,
Maybe the next movie is Don't Look Down.
Yes. Yes, there were people who were on roofs in Thessaly, taking videos.
Yeah. So anyway, thanks very much. And I'll continue my online following.
Okay, great. Thank you.